Alright, we had looked at Lewis structures as a tool for predicting the behavior of atoms, whether they'll gain or lose electrons and how many electrons they will share to form bonds. And the Lewis structures are very powerful tools to understand small molecules or small ions, as well as larger molecules once we look at big organic compounds. And the Lewis structure is basically going to tell us where the valence electrons are. So, in the old days, we used to look at things intuitively and try to piece together a Lewis structure for a small molecule or ion by thinking about how many bonds each atom wanted to form and see if we could sort of figure out the best distribution. But sometime about 20 years ago, some instructors have come up with this sort of 5-step procedure to draw a Lewis structure for small molecules or ions. And as long as I'm using this 5-step procedure, I get the right answer every time, pretty much. So I don't like guessing. I don't like having to try to guess where multiple bonds are. So as much as I might not like following algorithms or directions, I'd rather understand things. If you follow these 5 steps, you get the right answer, and so that's pretty powerful. So what I would ask you to do is commit these 5 steps to draw a Lewis structure to memory, and then I will do a few examples of drawing Lewis structures for small molecules or ions so that you get a little practice drawing them. And then if you master these 5 steps, you essentially master Lewis structures for small molecules or ions. The first thing that's absolutely critical, and I've seen a bunch of procedures, and it doesn't matter whose procedure you look at, determining the total number of valence electrons is absolutely critical. If you don't have the right number of valence electrons in your Lewis structure, you can't have the right answer. So that's absolutely totally important. The next one is perhaps the easiest thing to do in chemistry, because you're going to connect the atoms with single bonds. And since doing that essentially is just done by drawing lines between the atoms, all you have to do is draw lines between the atoms. And the hard part about this one is sometimes you have to know the connectivity, which is the central atoms which are attached to what, but we generally give you that. So if you know the connectivity, then putting things together with single bonds is super easy. You just draw lines. And you'll see that when I do examples that the second step is pretty simple, but it's very important because everything needs to be bonded to the rest of the molecule. So connecting atoms with single bonds, super important. Then we're going to fill the octets. A more technically accurate term might be fill the valences, but a lot of times that is too confusing for people. Octets, fill the octets mean that if you have a non-central atom other than hydrogen, you're going to want 8 electrons in its environment. So again, this will make more sense when I do examples, but if you have a typical nonmetal in a Lewis structure that's covalently bonded to the central atom, you're going to want 8 electrons in its environment. If it's hydrogen, it obeys the duet rule, so you fill the duet for hydrogen. Again, that's hopefully going to be something you've seen before. If not, a little practice will go a long way. And then after you're done filling the octets on the non-central atoms, you might have more electrons you need to put in to your molecule or ion. So at this point, it's a good idea to count the number of electrons you've used to make the single bonds and to fill the octets. If you still have electrons that are not in your picture, you place the unused electrons on the central atom. And this is where you might have to violate the octet rule. If the central atom already has 8 electrons around it and there's still electrons, you just add them to there and you might end up with 10 or 12 electrons on the central atom. In organic chemistry, you usually don't violate the octet rule. A little more comfortable, but certainly with some inorganic compounds, you're going to have more than 8 electrons on the central atom. Alright, and then if the central atom, and this is one of probably my favorite step in terms of a big advantage of using this procedure, is we used to sort of guess where the multiple bonds might be. to try to make everything work out. This gives us a procedure. If the central atom has fewer than 8 electrons in its environment, then what it does is it asks its neighbor to share with it. So you have a neighboring atom share electrons, share a pair of electrons with the central atom, making multiple bonds. So if it shares one pair, it makes one multiple bond. If it shares more than one pair, you get more than one multiple bond. You get triple bonds or 2 double bonds. And so this one tells me that I'll have multiple bonds if after I place the electrons in the most logical places, the central atom still doesn't have enough electrons, then it has to force a neighbor to share more with it, and that'll make the multiple bond. So just memorize these 5 steps. Determine the total number of valence electrons, connect the atoms with single bonds, fill the octets on the non-central atoms, place unused electrons after the second and third step. If there's any electrons left over, you put them on the central atom, and then after the fourth step, if the central atom still doesn't have enough electrons around it, it needs 8 in its environment, it'll essentially force a neighboring atom to share with it, making multiple bonds. Alright, so let's see that in action. Very good example is nitrite, right? Nitrite with an I. Hopefully you know that nitrate is NO3 minus, and the ite in a series always has one fewer oxygen than the 8 in the series. So nitrite would be NO2 minus, NO2 minus. So that's the formula that we would go with to start the Lewis structure. The first step was to determine the number of valence electrons in nitrite, not nitrate. So nitrogen, if you look at just the nitrogen atom, is 5 valence electrons, S2P3. So we're going to put 5 electrons from the nitrogen into this picture. You have 2 oxygens, and each oxygen brings in 6 valence electrons. And then the way something gets to be negatively charged is to gain an electron. So we have 5 electrons from the nitrogen, 6 from each of the 2 oxygens, and 1 to make the negative charge. So 12, 13 plus 5, we have 18 electrons that need to go into the Lewis structure to have the right number of valence electrons. Second step, my favorite. I have a nitrogen and 2 oxygens, and I connect them with single bonds. So super simple. And you do have to put the nitrogen in the center and the 2 oxygens on the outside to get the right structure. Some people would put NOO, to which we say no, right? And so you need the nitrogen in the center and the 2 oxygens on the outside. The third step, I'm not going to bother to redraw this, because the third step is, right, to put the electrons, the non-central atoms, to bring the electron count to 8 electrons in the environment of every non-central atom. So if you look here, I have 1, 2, 3, 4, 5, 6, 7, 8 pair of electrons in oxygen's environment. So in oxygen's environment, I have 8 electrons because I added the 6 to the bonding pair that was already in oxygen's environment. I did the same over here. So at the end of the third step, I put in the 2 single bonds and the 3, 4, 5, 6 pairs of electrons in the molecule to fill the octets of the non-central oxygens. And so now I want to count and say how many electrons are in this picture now. 2, 4, 6, 8, 10, 12, 14, 16 electrons after I connected the atoms with single bonds and filled the octets of the non-central atoms. I need to have 18 electrons in the picture, so I've got to add 2. And the fourth step says I add those 2 to the central atom. So now I have 18 electrons in the picture, 2, 4, 6, 8, 10, 12, 14, 16, 18. And I'll be careful not to put the pencil to the page too many times because I'm adding extra dots. But you can see I now have 18 electrons in the picture. The problem is this nitrogen has only 6 electrons in its environment. The nitrogen has 2 single bonds and the lone pair, 2, 4, 6 electrons in its environment. It needs to have 8. So what the nitrogen is going to do is force the oxygen next to it to share with it. So when nitrogen over here with only 6 electrons in its environment sees that oxygen has all these unshared pairs, it says, hey, can I share? And what the organic chemists do to show reaction mechanisms and changes that occur in molecules or ions is they use these electron pushing arrows. And what this is saying is that this pair of electrons that's only on the oxygen is going to be shared, and I might actually draw it a little differently to emphasize where it's going to go. But this pair of electrons is now going to form a bond between the nitrogen and the oxygen. And a lot of times I like to use intelligent color. I'll have different color markers on the board or different color pens on the paper so that I can show that this new bond is formed from these electrons moving over there. So I might draw this arrow in red and then draw a red line for the new bond so that your minds can focus on the color coordination of the new bond being formed. And notice when I move the pair of electrons from the oxygen to being shared, it's still in the environment of the oxygen. So this oxygen has 2, 4, 6, 8 electrons in its environment, obeying the octet rule. This nitrogen now has 2, 4, 6, 8 electrons in its environment. So excellent octet rule. This oxygen has 2, 4, 6, 8 electrons in its environment. So super good now. We were obeying the octet rule for each element. We've got the proper number of electrons at 18, and we're obeying the octet rule. One of the things that if you're taking general chemistry at Glendale Community College, you would know that if we have an ion, we're supposed to put the Lewis structure in brackets and show the overall charge. So that's a really good Lewis structure for nitrite, and that's what we get for following the 5 steps. Gives us a good sort of award-winning nitrite dot structure. Now, back in the old days when somebody produced this dot structure for nitrite, a crystallographer or somebody with some experience in determining the structure of molecules would look at this and say, this is wrong. And the reason they'd call it wrong is because the double bond is predicting or indicating that the nitrogen-oxygen bond on the left is going to be shorter and stronger than the nitrogen-oxygen bond on the right. So single bonds are weaker and longer. Double bonds are shorter and stronger. So this indicates that the 2 bonds between nitrogen and oxygen are different lengths and strengths. If you look at the structure for nitrites, they're the same. So what people did to sort of get around that little difficulty, this individual structure suggests the left bond is shorter and stronger, the right bond is longer and weaker. The reality is they're equivalent. So, but if you look, we formed this structure by making the left oxygen share. We equally could have made the right oxygen share. So if this guy, this oxygen to the right, had shared a pair of electrons, then the double bond would be to the right instead of to the left. So if I draw essentially the mirror image of this structure with, again, still the overall negative charge, one oxygen is double bonded, the other is single bonded, but now we've let the other oxygen be the double bonded one. Now if you look at the left oxygen is the double bond half the time, the right oxygen is the double bond half the time, so now they're equal. So what they decided to do is draw a pair of structures for this particular ion. They call them resonance structures, and the real structure is seen as an average of these two. So rather than having the double bond to the left or the double bond to the right, the double bond is averaged between the two bonds. So it's like each NO bond is like a bond and a half. So shorter and stronger than a single bond, longer and weaker than a double bond. Because it gets to be the double bond half the time, it's the single bond half the time, so it's sort of between the two. So here's an example, nitrite, where I had to employ all 5 steps. The right number of valence electrons, connecting the atoms with single bonds, filling the octets of the non-central atoms, putting any leftover electrons that I didn't put in the picture yet on the central atom, and then when the central atom had less than 8 electrons, I had to share some electrons from a non-central atom. And this again, the key thing I love about the 5th step is when you're doing the 5th step, if the central atom has fewer than 8 electrons, you have to have a neighboring atom share electrons with it. If there's multiple ways, multiple atoms that can share electrons, or multiple ways to share those electrons, then you have resonance forms. So I used to always wonder, in addition to when do I have multiple bonds and how many multiple bonds, the 5th step sort of tells me when I should have multiple bonds and why. I always wondered, like, how many resonance forms should I draw? And that'll totally depend on how many ways there are to do the 5th step. So when this guy was short a pair of electrons, I could either have the left oxygen or the right oxygen share 2 ways to fulfill the octet of the central nitrogen, means 2 resonance structures. And we'll do a couple more complicated examples, which will take some time, to show things like formal charge and other things that allow us to predict properties of atoms and ions from the dot structures. But this was just your basic, like, 5 steps to draw Lewis structures with one good complete example. I hope it was helpful for you. We'll do more.